are going to be a little bit of a survey and somewhat of a tutorial. I wanted to tell you a little about these lifting theorems and then actually try to give you most of the ideas in the proof of this BPP lifting theorem with Mika and Tom. Okay, so everybody knows what communication complexity is, and randomized communication complexity. So just I don't have to preach the converted communication complexity. We all love it. That slide too. So lower bounds for communication complexity. It's going to be real fast. Okay, so lower bounds. I'm going to focus on this third method, obviously, this idea of hardness escalation, or a way to use function composition to go from a decision tree or query complexity measure to the corresponding communication complexity measure. Okay? So that's what I'll talk about today. And the basic intuition behind this is that if we just look at the functions that are like the typical, poster child functions in communication complexity, they're all composed functions. So the equality function, Alice and Bob, Alice gets x1 through xn, Bob y1 through yn, and you want to know if their strings are equal, and this is just a big OR of so f, the outer function f is an OR, and the inner function g, which I'll call a gadget, is just a parity function on 2 bits. Okay, and likewise, set disjointness, gap handling, inner product, they're all sort of this type composed functions. And f I'll always use to refer to the top function, and it'll have n wires feeding into it, and at the bottom you'll have repeated copies of a gadget g applied to disjoint inputs, and we like the inputs to G to be as small as possible. Oh, and one thing that's important is in the communication problem, for each copy of the gadget, the inputs to the gadget will be partitioned into 2 pieces, so Alice gets half and Bob gets half. Okay, and what we want to do is, in general, come up with a theorem that says that as long as I get to pick the gadget, so as long as the gadget is sufficiently hard, that we can study the communication complexity of the composed function by studying the corresponding query complexity or decision tree complexity of the base function. Okay, so for example here, the top level function is OR, and the decision tree complexity of OR is linear. You have to query all the bits feeding into F, which is linear, and correspondingly we'd like to show that the communication complexity of set disjointness, which is the lifted version of the OR function, where the inner gadget is, and that has corresponding complexity linear. Okay. So the easy direction is, assuming the gadget is small, the easy direction is to show that once you have a decision tree for F, you can just mimic that decision tree to come up with a communication protocol for the lifted function. Okay, so here's the dumb decision tree for OR, but in general, if you have a decision tree for your outer function, the 2 players, Alice and Bob, just follow this tree. So given that the first bit of F that's queried is Z1, they'll run a little protocol to compute G on the corresponding bits X1 and Y1, and depending on the answer, go left or right, and so on. So the communication complexity will be whatever the best protocol is for one of these little gadgets times the height of the tree. Okay. So that's the easy direction, and the hard direction is to show the other way around, that from a protocol for the composed function, you actually can extract a decision tree. Okay? And there's many flavors of this. This is the deterministic version, but you can modify both sides. So you can talk about randomized protocols and randomized decision trees, and et cetera, et cetera. Okay? Good so far? Okay, so there's been quite a lot of work. It's been an active area. I'd say it started with these top 2 papers by Scherstoff and Roz McKenzie, and now there's lifting theorems in a wide variety of contexts. I'm not going to say too much about them all. But once you have one, it's really good because you can prove upper and lower bounds quite easily now. So it's good not just for getting lower bounds, but for getting separations between classes. Because once you have the lifting theorem, let's say you want to prove, all you have to do is prove, study the query complexity of some base function that gives you whatever separation you want, and then just apply it in verbatim with the lifting theorem, and you automatically get the same result in the communication world. So it's called lifting because or escalation because you're kind of translating a lower bound in a simple model to a lower bound in a more complicated model. Okay. Or said the other way around, you're kind of showing that in the communication world, the only thing that you can do is like the obvious protocol. Okay. And there's been lots of applications. Mika will talk some about extending these ideas to a DAG version of communication complexity. I think that's what he's going to talk about, and how to get monotone circuit lower bounds from that. Some of them are new. The Roberts lifting theorem, you can apply it to get new results about linear secret sharing schemes. It's really exciting work in extended formulations where they use lifting theorems in that context to prove, very strong exponential lower bounds on deterministic and even approximate algorithms for extended formulations, and so on and so forth. So there's lots of applications of this. But I mostly just want to get to the theorem and try to give you an idea of the proof. So the theorem roughly is that I'm going to pick the gadget, and it's the same gadget that's been used a lot. It's the original Ross-Mackenzie gadget. And I want to show that no matter what f is, f's the outer function. And I want to stress that f, it might not be a function, it might be a search problem or partial function. And that's really important in the applications. So it's really important that f is like pretty much completely generic. So I'll call it a function, but it really, in the applications, it's often like a search problem. Okay. So we want to show that the randomized decision tree complexity of f times the log n overhead, which is what's going to be required for them to compute one copy of the gadget, that's roughly equal to the randomized communication complexity of the lifted thing. Okay. Okay, so here's the gadget. So it's called the index or pointer gadget, and this is a picture of the gadget, one copy of the gadget. So in general, f is going to have n inputs, and the gadget is not going to be constant like it was for and or parity. It's going to be bigger than that. In fact, one side, it's going to be asymmetric or uneven. One player is going to have order log n many bits, and the other player is going to have like n to the third or n to the, I'm saying n to the 100, but something like n to the third bits. So Alice gets a string of length log m, and Bob gets a string of length m. And this is sort of like a universal gadget because it can encode any function. This is like a truth table of a function, and this is like asking. This is like an index. So it's asking what's the value of this function on this input. Okay. No? Good. Okay. Yeah, interrupt me if you. It's good. Okay. So again, you might think this is weird because Bob's string is so big. So when we do this composition, we have an outer f, and we have to feed in. So f originally had variables z1 through zn. Now we replace each zi by tons of variables. So order log n times n to the 100, which is a lot more variables. It's still polynomial in n. Okay, but you might think, well, this is a big problem. How are we going to get this? But the point is that in any lopsided thing, the trivial protocol is that the person with the shorter string just sends the string to the other player. And since this is order log n in length, that's where this is coming from. Okay? So even though one side is quite long, it doesn't really affect anything. So we measure, it's like what's important is the size of the shorter string. Okay, so just to tell you, I think probably you know, but I'll tell you what a randomized decision tree is. So it's just, you can think of it as either a distribution on deterministic decision trees or as a single tree that has coin flip nodes and query nodes. So this is a single tree that has coin flip nodes, and so you go this way with probability p and 1 minus p, and then you have query nodes that query variables. Okay? And for every assignment to the z variables, this gives you a distribution on leaves of the tree, and the leaves are all labeled 0 or 1. And you say that the tree computes f if for every z, the probability that you get the right answer over the distribution of the leaves induced by a particular value z, you get the right answer, say probability 2/3. And the height or the complexity is you're just counting the query nodes, so you don't count these nodes. Okay. Okay, so just to remind you what we're trying to do. We're trying to do the hard direction. So we're trying to show that from an arbitrary randomized communication complexity protocol for the lifted function, we can extract a randomized decision tree whose height is not much different than the original number of bits sent over here. Okay, and we're going to restrict attention to deterministic. You'll see why this is not really a restriction in a minute, but we're going to restrict attention to deterministic protocols over here, but we're going to simulate them so well that a randomized protocol, which is just a distribution over deterministic protocols, it'll work for each one, so we'll end up with what we want. Okay, so how are we going to prove this? And this is how, when I say how we're going to prove this, I mean like I want to give you a constructive proof. So actually like an algorithm for given an arbitrary protocol actually gives you the randomized decision tree. Okay, so first of all, we're just going to, since we don't know anything about f to begin with, we can't really use anything about f. So we're just going to ignore f altogether. Okay, instead of thinking of pi, so pi is a deterministic protocol for the composed function, but we're really going to think of it in terms of how it partitions the inputs to f. Okay. So let me draw you a picture here. Hopefully this will maybe help. If not, please interrupt me if this doesn't make sense. So this is capital X is all possible inputs to Alice. Okay, so she has n times log m bits. Okay, so it's 2 to that. And Y is all possible inputs to Bob, and his is like m times n many bits. Okay, and so I'm going to think about so each of these points in here. Okay, it's labeled with a. So we apply each gadget to it, and that gives us a vector of length n. So we'll call that a z vector. So it gives us, when we apply, this should not be -1. So this is like, this should be g to the n of xy. So we apply, x is broken up into n pieces, so is y, and we apply g to each copy. That gives us an n-bit string z. Okay, so we're just going to think about, so these colors correspond to, this is all the inputs, all the pairs xy, where the corresponding z string is the same, some particular value, purple. Okay, and this is another one, and so on. Okay, it might not look like slices, but it's just to sort of show you that they're all kind of hopefully distributed really nicely. Okay. Okay, so we're going to think of this whole space as partitioned into these z slices. Okay, and we're really going to think of the whole protocol with respect to what it does, how it deals with these z slices. Okay. Questions? Okay, so this is a picture of the protocol. Remember, it's a deterministic protocol. So, in this case, this blue line means Alice spoke first, partitioned her input into 2 pieces, and then Bob spoke, and so on. So these are all the rectangles that were induced by the deterministic protocol pi. Okay, and again, I don't care about the value of f on them. What I really care about is how each z slice is distributed relative to them. So this is a particular z slice. So these are all the inputs x, y, consistent with a particular vector of length n. Okay, and when you run, so imagine that for a particular value of z, like the all zero string, imagine that you're going to run the protocol pi over all uniformly. You're going to run it over all the xy pairs in this slice. Okay. And think of that as being a uniform distribution over them all. So that's going to give you a distribution over the transcripts of the protocol, right? So, so this transcript in particular, it's like, I don't know, maybe like a quarter of the time you end up in here. Okay? So this transcript will have probability like a quarter with respect to the z slice, and so on. Does that make sense?
Sorry, so you're picking a random point on the slice and looking at what's the transcript?
Correct. Right. And that gives me a distribution. So for every z, I get a different distribution of transcripts. And for the purple one, wherever it was, that would be where I would run the protocol over the distribution of purple ones. And what I'm going to try to do is come up with a randomized decision tree that's, instead of labeling the leaves with the value of F composed with G, I'll just label the leaves with the name of the transcript. Okay? And what I'm going to want is that for every Z, that the distribution of transcripts induced by running this protocol pi on the pink slice is going to be the same, or roughly the same, as the distribution of transcripts induced by running the randomized decision tree on that same Z value. That was maybe a mouthful, but that's what this is. So we're going to make a randomized decision tree. The leaves of the decision tree are going to be labeled with transcripts from pi, the communication protocol. And remember, it's a randomized decision tree, so for every Z value, and it's a decision tree that queries the Z's. Okay, it only queries the inputs to F. And for every Z value, therefore, you get a distribution on leaves, which is a distribution on transcripts. And we want that to be basically, that's what I'm calling this. This is the decision tree running on Z. It gives us a distribution over transcripts. And I want that to be roughly the same for every Z as the distribution of transcripts that would be induced by, running the original protocol on a random XY, with corresponding value Z. Does that make sense? If that makes sense, we're a good portion of the way. If it doesn't make sense.
So being Boolean is not relevant here, you can just have different values.
Correct. You mean for F?
Yeah.
Correct, yeah. F is usually, in the applications, it won't be Boolean. It doesn't even enter in. Any questions before I? Yep.
What kind of closeness do you want about?
Yeah, so I want it to be like, I don't know, something like 1 in polynomial in n for every Z. 1 over n to the third, maybe.
And L1 for statistical distances.
Yes. Okay, so what can we possibly do? So here you are. Imagine now you are the person, you have the protocol in front of you. You know exactly how XY was partitioned. You have this you know this picture, right? This picture, but you don't know. You have a Z value, but you haven't. You can only look at bits when you query them, so you don't know anything about which slice you're in initially. Okay, and we're trying to, step by step, look at the protocol. So the communication protocol, the first thing it does is Alice spoke first, partitions this into 2 pieces. Step by step, we're trying to mimic this with a randomized decision tree that's only allowed to query the bits of Z. And we don't want to query the bits of Z. We want to query them proportionally to the length of the protocol on the left. So there's really not a whole lot that you can do in the beginning. So Alice, and we want the distribution of transcripts to kind of be identical. Okay. So what can you do when you know that the first thing that happens is this, and you don't know anything about the pink? Well, it seems to me the only thing you can do, unless you know something about F or whatever, is that you can go to this side proportional to the size of this subrectangle, and this proportional to the size of this subrectangle. And if you're really lucky, the distribution of XY is in here, the marginal on the X side will be really close to uniform. And again, the marginal of the pink thing on the Y's will be close to uniform. And if that happens, then when you go left and right with probability proportional to, to the protocol, that'll preserve the probabilities. Okay. So that's the whole idea. We're going to always go left and right with probability proportional to the sizes, what we know, but we're going to have to keep track of some measure that's going to make sure that this is going to happen, that our marginal distribution within the pink for every pink slice is kind of roughly uniform over the current rectangle X's and the current rectangle Y's. Okay.
You didn't say which variable you would query.
I'm not querying yet. Yeah. So I'm going to do this, keeping track of some measure of how much information I've learned about each coordinate. And when too much information has been learned about some coordinates at that point, so now I have to tell you how to do that. Yeah, you're, as usual, way ahead of me. So like the very highest level, we'll simulate the protocol, like I said, going left and right, just proportional to the size of the two pieces that were broken up by the communication protocol. Hopefully that hoping that works. But we're also going to keep track of, like I said, is how much information is revealed about the coordinates. And when too much has been revealed about a coordinate, at that point, we'll query the corresponding z bit, fix things up, and then restore our invariants and go on. Okay. So this is the invariance. And this is the same. The density is the same thing. Same invariant from the earlier paper by Mika and others that got a Junta lifting theorem. So again, X is always a subset of the set of all possible X's, and Y is a subset of all possible Y strings. So we're in a rectangle, X, Y. And the X part is said to be dense if the min entropy. So capital I is a subset of the n coordinates. Okay. So remember, we always view X as consisting of n blocks. So I'll call each block like a coordinate. Okay? And what we need for density is that for every subset of the coordinates, when you look at the distribution induced on those coordinates by X, the min entropy of that is, pretty big. Like the most it could be would be the size of I log m. So that's how many bits there are altogether. And we want it to be like a good fraction of that. Okay? So some constant amount of bits have been revealed, possibly about I, but not more than a constant fraction. And we want this for every I. And large is just to say up front, Y is such an enormously long string that it kind of sits along for the ride pretty much everywhere. So we don't really worry about it much. So this condition is more or less saying, so this is the min entropy, the total number of bits minus the min entropy is at most n to the third. So in other words, on average, only n to the third bits have been revealed. But Y is enormous. Each coordinate of Y is n to the 100 long. So this is nothing. Okay. So these are the invariants we want to maintain. And as long as these are maintained, we'll do what I said. As soon as this invariant's been, not met, then we'll have to take an action. Okay. So this just is a little less high level, but still very high level overview of the simulation. Simulate it going left and right as long as X is dense and Y is large. Whenever density is violated, now I have to show you what we do. And whenever largeness is violated, well, we just kind of halt and ignore it because it almost never happens. Okay, so this is the main step to figure out when density of X is violated, how we're going to fix those coordinates and correspondingly query those coordinates in the decision tree, and then that'll restore our invariant on the remaining coordinates. Okay, are you with me? Okay, so there's two things we'll need to show after I show you how we're going to, do this restoration. But there's two things I'll have to show you, and so I'm not going to say anything much about one thing we have to show you is the complexity, the decision tree we end up with, that the height of it's proportional to the height of the communication protocol. And I'm not going to say too much about it, but basically we don't do this restoration until enough bits have been revealed about the corresponding coordinates. So the fact that we already communicated a lot of bits in the protocol, well, it'll make it okay to do the density restoration. Okay, so it's some kind of a potential argument, but basically you're not going to query something until a lot of bits have been revealed. And then this will be the hard part, showing that the distribution on transcripts is going to be close. Okay, so this is how you do density restoration. So again, like I said, we're ignoring what happens if Y isn't large enough. So the only thing I'm going to worry about is if X loses density. So if X loses density, there's some maximal subset of coordinates, call it I1, where density hasn't been maintained. So this means that there's at least one value for all those coordinates that's too likely. Probably lots of values, but okay. So let's say alpha 1 is the actual value of all the coordinates. So we're fixing all the coordinates in I1 to some particular value that's too likely. Okay, and the x1 is the subset of X where I1 has been set to alpha 1. Okay, once you do that, once you pull out x1, x1 will now be dense because we took the maximal subset that wasn't dense. So people are quiet. So don't know if I'm going too fast or. I mean, yes.
So I have a general question. I mean, can I think of it as basically the protocol operates, then at some point some input of Alice, which is an index, is going to be fixed.
That's right.
Then also the corresponding bit
That's right.
of Bob will be fixed.
That's right.
And at that point, I'm going to query that.
That's right. Exactly. Exactly.
But actually, it can be more complicated.
It might not be one. It might be a whole bunch of.
Like a parity of the first 123 bits has been fixed, is close to being fixed, or something like that. Right?
That's why sometimes you might. That's why sometimes I1 might be enormous. It might not be just one at a time, because you might be computing parities of like 10 coordinates all at the same time, like Russell said, and so you might go for a long time, and then all of a sudden, at the same time, a whole block of coordinates. Too much is known about them. Okay, good. Any other questions?
Yeah, but you have an upper bound on the size of I just by the number of
N.
steps you've taken.
That's right. Yes, I'll get to that. I should have you up here, yeah. So anyways, you should think of this as maybe, I mean, it wasn't obvious to me before Mika said, let's do this, but now I think that this is like, you know, sort of obvious. But again, I didn't think of it. But I mean, basically, you need to restore density. So when density is violated, there's some set. Might as well take it to be the maximum. Might as well set it. This is perfectly dense. Then you have the rest of the stuff. Okay, so x minus x1. You move over here. You check again. Has density been violated? If so, you have another possibly different set of coordinates, I2, where density's been violated. Fix it to some 2 likely value. That breaks off another part, x2, and you just keep doing this until you have nothing left.
So what do you mean output x plus y equals up to output?
So I am partitioning x into disjoint pieces, each of which is now going to be dense.
But when you say you're partitioning, does that mean you're like, in the simulation, you're flipping a coin?
Yes, yeah, you're ahead of me. That's what we're going to do. Yeah. So I will describe the full simulation, but to do that, I have to first tell you how we're going to restore density. Yeah.
And these sets I1, I2, I3, they may overlap in various ways.
Yeah, yeah. I2 could be the same set of coordinates as I1 or a different set. Who knows?
But x1, x2, x3, they're partitioned.
Yes. Yeah, I mean, just by construction, because we took some stuff out, we moved everything else over, took some more stuff out. So when you do this, you start with x. That's, you know, I mean, we're always going to do this. After every step of Alice, we're always going to check, is x, remember when Alice sends a bit, it partitions the current x into 2 pieces. We'll go to each side proportional to the size. And then we check on both sides, was density violated? If so, we go into this process. Okay. So you can view this as like a refinement of the original protocol pi. So I'm adding more communication to it. So before, whenever Alice spoke, she just sent a bit. Now when she speaks, she sends a bit, and say left and right is 0 and 1. And now she's going to check to see if her density is violated. If so, do the partition, and then send the coordinate I. Current x has been partitioned into x1, x2, and so on. That partitions x, and she's going to send the corresponding bit I. Does that make sense? So this is like a partition. So in this case, say x isn't dense, so Alice has to break it up into a bunch of pieces, x1 up through x4. So just think of that as like refining the protocol. So we're breaking x up more. Now once that happens, at that point, we want Bob to speak. So we want him to now partition his inputs into 2 pieces based on whether, not 2 pieces, 2 to the size of, so let's say in x1, x1 just fixed, say 1 coordinate, okay? Then at this point, we want Bob to partition his inputs into 2 pieces. Those pieces were g. So remember, x1 fixes that coordinate. So now Bob's going to apply g, to his input on this fixed value for that coordinate, and that's going to partition y up into 2 pieces where g is 0 and where g is 1. And if x1 fixes like 10 coordinates, then Bob's going to have to send 10 bits.
Sorry, so now you're extracting a decision tree, right?
No, I am still just describing, I'm just describing this restoration process. That's really just, you should think of it as a process of refining the original communication protocol. So this might be look ugly, but I'm going to show it to you anyways. So this is the original protocol, okay? Nothing's going on here. This is just, either Bob sends the next bit B, and then we update, the rectangles, or Alice sends a bit B, okay, and then you update the rectangles. That's the typical original protocol. And now, like I said, we're refining this so that now when Alice sends a bit B, that partitions X into two pieces, and now we're going to check for each of those pieces whether density was violated. If so, she's going to send more information. She's going to partition her current X up into all the different pieces and say which one the current X is in. Okay, so she sends this bit I, and then Bob is going to send a corresponding message S that's going to partition the Y up into all the possible values that G could have on the fixed stuff that was set in Xi.
What is I sub I?
Yeah, sorry about this bad notation. I have a better picture maybe. Okay.
Yeah, that's good.
Okay. I'll get back to another picture of it. So again, I'm just thinking this is refining the protocol. It could add a lot of length to the protocol, as a lot more bits could be sent. And I told you before, I'm not going to worry about that for now. Okay, so I just want to show it's not going to be a big deal because these bits are only going to be, this extra stuff's only going to be sent when a lot of stuff has already been learned about these coordinates. But what I want to do is show you what the full randomized decision tree simulation.
Is this refinement sort of needed, or is just a more convenient?
It's needed.
It's needed? I mean,
Well, okay. I don't mean it's needed to prove the theorem,
No,
but it's needed in the
you can
proof.
extract the decision tree by just going into the right part.
No, because we don't forget when a coordinate has been too much about it's learned, we have to fix it to a value of 0. At that point, we're going to query the decision tree, just like Emmanuel said. So we want to query the corresponding coordinate, and we want to go left if it's 0 and 1 if it's 1. So we have to, at that point, fix, partition the X and the Y up, into pieces so that whenever you queried left and that coordinate, the G value is 0, that all the X, Y are consistent with that, and likewise. Same thing that you do.
You need to maintain the invariant. Without the invariant, you cannot
No,
guarantee that the probabilities of the
understand.
remaining protocol.
The whole reason for maintaining the invariant, I think the whole reason for maintaining the invariant is because we want, when too much information is learned, at that point we want to really fix, break up the X, Y so that it's now consists of a bunch of rectangles, each of which on that coordinate are fixed to be 0 or 1. Each of those rectangles should be monochromatic on the fixed stuff. So that was, okay, so here's the simulation of this extended protocol on a Z. It's just what we said. Whenever Bob sends a bit, that breaks up Y into two pieces, and we go to each side in the decision tree with the appropriate probability, with the same probabilities, hoping that the marginals are the same. Okay, and likewise, when Alice sends a bit, we go proportional. And again, here now Alice, if she ever has to refine her X and partition it, then again, we're going to go to, in the decision tree, we have to decide what to do. So we're going to, again, randomly go to the piece I with probability proportional to the size of the ith piece in the partition. And then here, let me just finish it off. Here, when Bob sends S, at that point, this is where we're going to actually query the corresponding bits, corresponding coordinates, the ZI values, in the decision tree. Okay, and for a particular Z, this is going to be a deterministic step. Okay, because Z has a particular value, so we'll go left or right depending on.
So which Z's do you query?
So this is, Z is like the input to F, okay, and here I'm going to query, so over here, when X was broken up into pieces, there were some coordinates that were too likely, say coordinate 1 and 2. So then I'm going to fix this whole process here in pink, the whole point of it is to break up x and y further so that each piece is fixed to be, the coordinate 1, 2 together are fixed. So there's the 0, 0, 1, 0, 1, 1, 0, 1, 1. And those are the two coordinates that we're clearing over here.
So the top three purple things, they're just dice rolls, basically.
That's right.
They're
Everything's
not
just
touching it, but-
everything is literally just, so you take the, implementation-wise, you take the original protocol pi, you turn it into this protocol, which is easy to do, just refine it, okay? After you do that, then literally the simulation is just to always go proportional to the size. And whenever, except for this step, when Bob finally sends this bit, then that's when you query the corresponding coordinates and go according to your z.
So can I think of this result as saying that any protocol can be written in a certain way that so any communication protocol can be refined in a certain sense where each rectangle now has a certain structure, meaning that in each new rectangle some coordinates are fixed and some coordinates are wobbly.
And then the rest of it, so I didn't say this, but when you fix some stuff, then the whole argument, when the whole measure of dense and large is always with respect to the unfixed ones.
So what would be the claim of that any protocol can be refined so that every rectangle has some coordinate fixed and some others are high entropy or something? I don't know.
I'm not sure.
Something I want to consider.
So we're simulating the protocol on the left, and we're always maintaining that every rectangle, the x part is dense on the unfixed coordinate, the y part is large.
Okay, so.
And because of that, if that property is maintained, it'll turn out that no matter what z is, when you go I'll show you this in a second, but when you go proportional to the size of how the split is, it'll preserve up to a one inverse polynomial in n. It'll be correct within that probability. So I don't know if. So this doesn't say much. This is just saying the whole job is to show that this distribution over transcripts that I talked about in the beginning. So for every z, for every vector of length n, you have two distributions on transcripts. One is the one where you ran the protocol pi or pi bar over a uniform element xy that, where the gadgets on xy give you z. And the other one is when you run the decision tree on z itself. Okay, we're trying to show that those two are really close to each other. And this lemma is just saying, well, we can do this, node by node or step by step of the protocol. So we're going to look at when Alice sends a bit, followed by density restoration, followed by Bob sending his bits for if anything had to be fixed. That's going to be considered like one step or one phase. And we're going to show that for every phase, that the distribution of the two messages sent in that phase are close to each other, and then we'll stack them all up using a coupling argument to show that the whole thing, that implies that the whole distribution, that the difference between the transcripts on the whole distribution is maintained. So we just want to have to show message by message or round by round that if things start off well in this round, Alice sends one bit followed by one density restoration step followed by Bob sending his bits, that the little distribution on messages on that little round are going to be close to each other.
And you can afford to give a lot of information about why, because...
Exactly. So that's what I wanted to tell you. So I'll get to that in a second. So the main lemma that's going to make let everything go through, in addition to the fact that y is so huge, is this uniform marginals lemma that's saying as long as our invariant is true, so we're currently in a rectangle xy, and as long as x is dense and y is large, then we get what we want. For every z value, this is if you looked at the distribution in the z slice that intersects xy, the marginal on x, that's going to be close to uniform on x, and likewise for y. So remember I said that we're going to have an invariant, and if that invariant is maintained, then we'll be able to, then when we go proportional to the sizes, it'll be good. So this is exactly what's the lemma that's going to give us that. And I'll postpone this for a minute. So again, just two things about lemma 6, which is, so again, we're going to fix the z, and we're fixing v, which is a vertex in the protocol. So it's like one place in the protocol where Alice is about to send a bit. And we're currently at some rectangle x cross y. This is not the whole thing, but it's some subrectangle that I'm going to call x cross y again. Okay, some subrectangle. And I'm just going to, for now, assume that everything's perfect so far. So I'm not going to worry about mistakes that have happened already. So that let's say so far that the distribution, so the xy distribution over the current rectangle is pretty close to, the x part is pretty close to the distribution x prime and y prime, that's induced by the xy's in the z slice. Okay, so in other words, the transcript so far, the message is sent and so far leading to this vertex, I'm assuming that like nothing bad's happened so far. Just the same that everything's perfect. Okay, so I just wanted to give you just the two ideas for why everything's going to be good in this next round. Okay. So this is just a picture of one communication step where Alice speaks. So we're at some vertex v in the middle of the communication protocol, the refined one. So v is some vertex in the refined protocol. Alice speaks. She sends a bit 0 or 1. Okay, that partitions x into two pieces, and now she possibly has to do density restoration. So that was the original x cross y, and when she sent the bit b1, maybe this is b equals 1/2. Okay, and then when she does density restoration, that partitions this into pieces, right? And each of those is now dense. And then she sends the name I of one of these pieces, say this one. Okay. And then Bob sends his bits, and if this density restoration only, so let's say all it did was work on one coordinate. So that would give you a partition of y into two pieces, where that all the inputs where that coordinate was 0 and where that coordinate is 1. More generally, this could be partitioned into, 2 to the s pieces, depending on how big I is. So anyways, after this step, Alice sending a bit, and then sending the partition, and then Bob further refining the y's, we finally end up with, all of these little, this whole space has been partitioned into these pieces. Okay, this is now monochromatic with respect to the fixed coordinates. Okay, so all the fixed coordinates are set, the values of them are set, have value s, and everything's dense, and this is dense. Okay. So basically, by the uniform marginals lemma, when you're at this point, these two are going to be close to one another. Because remember, what we did was we went here with probability proportional to the size. We went to this side with probability proportional to the size, and then here with probability proportional to the size. Okay, and when we did that, this was dense in x, so we can apply the uniform marginals lemma, assuming that y is fine, which I assumed it was in the beginning. So since we applied it at this point, the new part of the so the messages, the two different messages, are going to be very close to one another. Okay, so then we just have to. So what's bad that could happen? So what's bad that could happen is if the y part here. So we're going to query. Remember, at this point, after this phase, we're actually going to, in the decision tree, we're going to query these coordinates. Okay, now it could be that for some value of those coordinates, there are no strings. The rectangle's empty here. And that would be bad. That would lead to error. Okay, but what Avi said was that, basically, this entire tree, okay, just look at the whole possible tree and how many leaves it could have. Okay, and x is so small compared to y that the total number of leaves it could really possibly have is like exponential in something like n log m. And that's really tiny. So the number of bits revealed by this whole thing is like n log m. But since we chose m to be like n to the 100, that's really a small number of bits that are, revealed about y on average. So we're heavily taking advantage of the fact that y is so big compared to x to get that at every step the chunk of y that's left over in each of these pieces is significant in size. And then we're using the uniform marginals lemma to argue that that the two messages are going to be about the same. I thought this would be easier to do in an hour. So okay, so just want to say a couple things about this uniform. Do you have any questions? Should I summarize where we're at? Okay, so I described the protocol. So you start with the original CC protocol, you refine it. I described this process of making the decision tree that's randomized, and and it was a little bit, refining the protocol was the complicated part. Once we did that, the decision tree that corresponds to it is easy. You just always go everywhere with probability with the same proportion, and except in that one step where you finally fix those coordinates, and in that case you make the queries. Okay. And what we have to show, what's left to show, is this uniform marginals lemma, that as long as we maintain that x is dense and y is large, then we'll have this property that we want, that the marginals with respect to the z-slice are going to be roughly the same as the uniform distribution. So it's the same thing, by looking at it, by using Fourier analysis, it's the same thing as showing this property that, so we're assuming x is dense and y is large, and we want to show that for every subset of the coordinates I, that the expected value, when you look at the distribution on x and y with respect to that subset I, okay, so we're picking a random x and y from this distribution, just looking at the coordinates I, that the expected value of the product of the GIs, this is just, so think about GIs being in 1 minus 1 for now, okay? And this is like looking at, the number of times it's basically the parity of it, whether it's, it's 1 times minus 1, so it's like the parity of G on all the places in Y. So do you remember what this is? This is like the index gadget. So X points to a location in Y, and we're doing this for all I and I. Okay. And that's giving us a bunch of values in 1 minus 1, and we want to know what's the expected value. And we like this expected value. We'd like this to be, very close to 0, okay, so that there's no bias towards 0 or 1. The parity is roughly half the time 0 and half the time 1.
Here, that x is dense, and y, what do you know from y?
Y just has to be large. So large meaning like, think of it as like all, of the 2 to the mn possible size it could be, the size of it is like 2 to the mn minus n to the third.
So uniform.
Almost full size. Yeah, just think of it as uniform.
Over a large set.
Yeah.
Okay. Thanks.
Okay, so I'm going to just try to say one word about not our proof, but a proof that Ryan came up with. I think it was independently just realized by lots of people. Okay, so there's this lemma in Ryan's book. It's called level K inequality lemma. And it states that if you have a Boolean function f from capital N bits to 0, 1, where the expected value is alpha, okay? So that means like the fraction of ones is alpha, and k is upper bounded by some quantity, then you can upper bound the sum of the Fourier coefficients squared for all characters s of size at most k. So it's like all the bottom Fourier coefficients, the sum of all those squared can be upper bounded by this quantity. It depends on alpha. Okay, so I just want to show you how once you have this lemma, how kind of the uniform marginal lemma follows pretty immediately from this. So this isn't saying much. So again, I is just some. I'm just really going to focus on the part of x. X has n coordinates, and you can think of I if you want as n, but it's just some subset of the coordinates, and we're dense, which means for every subset I we're dense. So I'm just going to focus on one subset I of the coordinates, and this is what we're trying to show. We're trying to show that this quantity, so this is the expected value. So now I switch notation, and x and y is just the distribution over the set of coordinates in I. So again, you could think of I as n. So x is, in that case, x would be, you would pick all, an arbitrary s from x, an arbitrary y from y, and here we're looking at, this is the value of the gadget, so, on each of those places pointed to. What?
Should be 0. The order.
Here?
Yeah.
Oh, well, this does end up being the value. So y sub I is like the value, so S is I think of S as a subset. So for each of the blocks, you pick one place. So that's like a subset of size I. Okay, and then y sub I would be the value of the gadget on each of those places.
This is the z value.
Yes, this is the z value. Yeah, so I'm looking at the parity of the z value. Yeah, and I want to say that the expected parity of the z value is, it's half the time 0 and half the time 1. So maybe it's better to look at it as a matrix. So here's the matrix version of the picture. On the top here are all the y's in my rectangle, and on the rows are all the x's, and I'm labeling an entry here. So an entry m sub sy, so that's just going to be, I'm going to multiply, I'm over 1 minus 1, so I'm just going to look at, so y is a vector. Maybe this helps. So here's like a vector y. So this is a vector y of length. If I is n, is all of n, and this is a vector of length mn. This is a particular y. It's broken up into these n pieces, and s is s is a particular element in x, so it's picking out one place in each of these. Okay, and the entry m of and this vector is labeled minus 1 1. Okay. Oh, sorry, minus 1 1. Okay, and so x picks out one location in each of these blocks, and I'm just multiplying them together, or I'm adding them up mod 2. Okay. And that's going to be the value of m of sy. Okay. So I'm just basically, it's going to be, it's going to be either 1 or minus 1. And what I want, so each of these entries in this is going to be 1 or minus 1, depending on whether the parity of that was 0 or 1, odd or even. And what I want is this whole matrix, when I take the sum of all these 1 minus 1 entries, to be really close to 0. Okay. So you can think of the corresponding. So I want to apply that lemma. So you can think of the corresponding function, which is that y is the ones of the function. Okay. So you have a function f, and the ones of the function are all the stuff in y. Okay. And since y is large, the expected alpha is that. Okay. And a row of this matrix is more or less going to correspond to the weighted Fourier coefficient of that function with the character s. So s, remember, I'm viewing s. So s is a collection of I pointers. So I can view that as a subset of mn of size n. So it's a size, it's size I, in this case I is n, size n character. So it's a subset of the coordinates. And so all this row is basically the Fourier coefficient of f corresponding to this subset, okay, but weighted accordingly to alpha. Does that make sense? Anyways, once you have that, it's really quite easy to apply the lemma, because each of the things in x its weight is at most the size of I, which I was calling k. So its weight is bounded. So you can just directly apply. The only thing that's different is that the lemma had these things squared, and we have absolute values, so you have to use Cauchy-Schwarz to get it in the squared form. So I'll skip this, but basically, you know, like I said, you first apply the claim. You know, each row more or less corresponds to the weighted Fourier coefficient, and then you just have to apply Cauchy-Schwarz to get it in the form of coefficient squared. And x has some of these characters of weight k, but we might as well just stick them all in there or whatever. And so then Ryan's lemma, or the lemma, the weight k lemma, tells you that this is upper bounded by this quantity, and then you use the largeness of y, which corresponds to this alpha, and the density of x to finally bound this. So it's probably too fast, but.
But even without this lemma, this intuitive,
Yeah.
Just from the intuition point of view, y is nearly uniform. Y is very close to uniform.
Yeah.
So every chunk is roughly balanced.
That's right.
And now, if x was uniform, you would pick just a random points at every block.
That's right. That's right.
That would be the Theorem.
That's right. The only thing is, like, you just have to make,
Decay exponentially.
Yeah, you just have to make sure that.
You don't pick a uniform place in every block, but it's nearly uniform.
Right. I mean, the only thing the only reason you don't get it immediately from like extractor is because you have many copies of it. So I think another way you could probably do it is by, well, the way that, yeah, by reduction to extractor. Yeah, I should have said this is like a sleek proof, but the basic intuition is exactly what you said. And it's also the same thing that's in some sense in the earlier proofs too, that use Ross-Mackenzie. In some sense it's very similar, the basic intuition at the end. So there's lots of open questions. I would be interested to know if there would be a lifting theorem for information complexity. Be great to make some progress on a constant size gadget. Occurred to me in this last 2 weeks that it would be of course the big open problem is to get these methods to work. We're starting to make progress on getting them to work for the DAG-like case, but really the huge problem is, you know, what happens when it's not monotone. So we'd like to these lifting theorems, when you apply them to circuit lower bounds, you always end up with a monotone circuit lower bound. And Robert sort of explained why. But it seems like it should be possible to get this to work in some setting in the non-monotone case. And it seems quite related to some of the earlier work on the KRW conjecture that uses, it's related to the proofs and actually there's implications that relate it to the proofs of the simplification of the KRW conjecture for these universal relations. So somehow I feel like there should be some more connections between the KRW conjecture and what's going on here. That's about it.
Any questions?
So how would lifting theorem for information complexity look like? Do you have any conjecture?
So I think it should just, I don't see why you couldn't just start with the same theorem, but just randomized decision tree to information complexity. In other words, I don't see why there should be.
What is left? Oh, just randomized decision tree.
Yeah, I don't see why there should be any difference between information and randomized for composed functions. Like the difference that.
Would it be like average number of queries though, rather than?
It's not quite
No,
that.
you just have to count the information revealed differently. I mean, you have to decide when you densify differently. That's
No,
But is this-
sorry, what's the?
Okay, so the problem is like information complexity. Along some branches, you might reveal a lot of information, and along other branches, you don't reveal anything.
I mean, the same thing's true about the bits here, no?
So saying that maybe you have to look at the average number of bits you reveal.
Yeah. Yeah, I don't know how to do it. I don't know how to do it.
Like
I see what
the
you're saying.
underlying object should be just like a randomized decision tree, right?
Yeah, I don't see why you can't just. Yeah, but I think you're already getting to what could be more complicated about the proof.
No, but it's like prior free information. Like
Well,
for decision tree.
Yeah. No, you're. I mean, yes. So because randomness is essential, you have to like either switch it to make it distribution free, or yeah, you have to work with the. I think maybe this is related to each other. Yeah.
So, but if you have like a conjectured form, right? You have F composed with G.
Yeah, I'll make the conjectured form that the randomized complexity of, the randomized decision tree complexity, maybe I won't say it's exactly, but like, close to the information complexity of the composed function. I don't care about the log n, or even if it's exactly right, but some.
Yeah, I wonder, it's somewhat technical, but can you, instead of the address functions, can you do it for the inner product function?
Yeah, great question.
And just do it dense?
Nope, don't know how to do that either. At least I don't think anybody yet knows how to do it.
So this asymmetry between x and y, where is that being exploited particularly?
So it's basically.
Y is very large.
So when we do this step where we want to make sure that, when Bob speaks and we want to make sure that that we can fix the bits, and that leaves us with these nice large things, that's heavily using the fact that Y is so big that so much information can be, this density restoring partition thing, it could just basically flat out like break X up into every single possible, like all possible, that's not going to happen probably, but it could do that and you'd still just be fine in terms of Y.
But is this uniform marginals lemma where you need density and marginals?
You probably, do you need it there also? Yeah, I think you need it there also, but I don't know where it's essential and where it's not.
Okay, any other questions?
Thanks.
Let's thank Toni. Yeah, so we'll be back at 4.